We should probably get going. Just bring this back up to the front.
That's awesome. Good morning. What a rowdy bunch. Good morning. Well, it is truly an honor to be here this morning. When I got the news, I was just so excited. Being a science geek, it's nice to be here. It's nice to have poet and playwrights in the room, Grant. It's good to have folks there as well. But as we all know, a hallmark of a liberal arts education are professors who are committed to teaching, and we certainly have that. And I think we all can point to faculty who poured so much into our students and are definitely committed to that engagement. What has impressed me since I've come back is the quality of the research and the commitment to research. And it just reaffirms what many of us know, that our best professors are also some of our best researchers. And so that combination of teaching and research is something that's truly outstanding. And it's something that, as we talk about recruiting the next generation of students, that's the thing that we talk about, that you're going to be exposed to some of the best scholars and researchers in the world. The person that I'm about to introduce is a great example of that. Nan Crystal Ahrens is a noted geoscientist. It was so exciting going into your lab and seeing that leaf that was how many years old? 65 million years old? Well, 67. What's, 65, 67, that's a rounding error, right? But 67 million years old, but a noted geoscientist. But also, I recall when I gave the convocation speech in 2016, address in 2016, she also won the award for the best teacher and best professor. And so, and it was just amazing to see that combination. But again, it shouldn't surprise us. And so I was so very grateful when Nan agreed to serve as our senior dean of the faculty, because I believe she represents the best of that teaching, research, and service. So without further ado, Nan Crystal Ahrens, senior dean of the faculty.
All right, good morning. So this is the sequence of introductions here. So it is my great pleasure to introduce Professor Penn, Professor Steve Penn from the physics department. And I wanted to echo one thing that President Vincent highlighted. What I tell admissions groups when I meet with admissions groups is that, a lot of times when you think about going to college to study science, you think about going to big research institutions where they have all the big toys and the fancy facilities and lots of graduate students and postdocs and so on and so forth. But the truth is that per capita, liberal arts institutions like ours produce more PhD students than do those large institutions. And it's because, and I was at one of those institutions before I came here, I avoided the undergraduates. And the reason I came here is because I want to work with them. And so one of the things that we do astonishingly well is allow our undergraduate students to, from their very first and second semesters, if they choose, to become involved in the kind of research that changes the fundamental way that we understand the universe. And that's what we're here to talk about today. So without further ado, it is my great pleasure, along with my colleague, Provost Lucas, to welcome you here today and to introduce Professor Steve Penn from physics, who will give us a little background on the announcement that we're going to be hearing live at 10 o'clock.
Thank you, Dan. Thank you, Greg. So here's the game plan for this morning. As was mentioned, we are going to segue into a press conference from the National Press Club at about 10 o'clock. I'm going to give you a short introduction before then. If we don't get all the way through, I'll come back to it when we come back from the press club. And that is a little bit open-ended. We're going to have to play it by ear together because I don't know exactly how long that's going to go or how long those questions are going to extend. Okay? So, because not all of you have seen one of my presentations before or been indoctrinated into why we search for gravitational waves, let me start off by asking that. Why is it that we search for gravitational waves? It's the same reason that when we look up into the night sky, we as the human race tend to wonder, how is the universe constructed? Are we alone? Where did we come from? When we look up into the night sky, is this all that we see? Is there something more? And for many decades and hundreds of years, we have built telescopes that are more and more powerful until the Hubble Space Telescope has been able to look out in this ultra-deep field picture. And all of the objects in this picture are all galaxies, each of which contain 100 billion stars. There are more stars in the observable universe than there are grains of sand on all the beaches on the earth. And yet, we can tell by how these stars and galaxies move that what we see is only about 4% of the total mass that exists within the universe. And how are we going to see the unseen? Einstein gave us a hint of that 100 years ago when he developed the general theory of relativity, where he was able to redescribe what we considered the force of gravity as the curvature within space-time. Sorry, my phone is ringing. That the curvature of space-time is due to the bending of space as a result of the concentration of matter and energy. That in a sense, we can see space curving, and we know that mass is telling space how to bend, and space is telling mass how to move. So you can describe the Earth-Moon system here as the moon moving within a warped space-time around the Earth. And it's constrained to move on the edge of that funnel of bent space-time that the Earth creates. And that is why it stays in its orbit. Or to give a three-dimensional representation, if this is the sun and a comet comes in, it responds to the fact that space itself is bent. And that is why it then moves and swings around the sun in its orbit. That the acceleration of masses produce a wave of curvature. So if I could take that sun and shake it back and forth, that it would then take this whole lattice work of space-time and cause it to vibrate and shake. And those waves would then propagate out through the universe. Now, making waves is something that we are familiar with doing when we talk about electromagnetism. We can move charges and create radio waves and light waves. Can we do the same thing with gravitational waves? Why do we have to search in space? So let's imagine this thought experiment. Let's take two 10 metric ton spheres of tungsten and separate them by 10 meters of carbon nanotube, which has the highest tensile strength of any material, and spin them at 100 hertz. And if you could do this on the Earth, which you can't because the materials would never withstand this strain, this is not sufficient to create a gravitational wave. The strain is only about 10 to the minus 39th, a billion hundredth. Then the reason for that is that if we look at the strain equation, what we find is that you have a factor of g, Newton's gravitational constant, over c to the fourth. So 10 to the minus 44. So gravity, while being the dominant force in the universe, is extremely weak. So if we ever hope to see gravitational waves, we have to be very sensitive, and we have to rely upon having the most intense masses moving at the fastest velocities and accelerations. Now, this has been observed before. So Halson-Taylor studied the binary pulsar in 1913-16, and what they found is that these two neutron stars are stars that are essentially gigantic atomic nuclei. Every tablespoon of their material weighs as much as Mount Everest. All of the space that would exist between the nucleus and the electrons have been gotten rid of as the matter has been crushed down into a star that is no bigger than Manhattan, but takes a mass that is 1.5 times that of our sun. And you have a pair of these that were orbiting each other at 4 million kilometers apart, going around a little less than every 8 hours, and their orbit would decay by only little less than 8 microseconds per year. It was losing energy. And what Halson-Taylor looked at is they said, maybe it's losing energy because of gravitational waves. So you see in that plot that's on the right-hand side that they map the decay of the orbit, and then they put on top of it the prediction for how much gravity wave energy they would radiate, and it just lies right on top of the curve. They won the Nobel Prize for this, and this was the first indirect indication that gravitational waves existed. How do we measure them? Well, gravitational waves move in a quadrupolar fashion. So if this were masses oriented in space-time, this is how they would move. They would stretch along one direction and shrink along the orthogonal direction, much as if I was stretching and shrinking an elastic material. But of course, you don't need this whole square of material. Really, all you need are 3 masses, and that is similar to an instrument that we use all the time in physics called an interferometer, which takes laser light from a source, splits it up, reflects it off of mirrors, and as it comes back to the beam splitter, if these sides are exactly the same, I get no signal. But to the extent that they're different, I get a signal. So here's the light wave going out, reflecting off of the mirror and coming back. And as it comes back, if it's in phase, I get no signal. But the degree to which this is slightly out of phase, you can see now the mirror is about to move out of phase, I get a signal here. So as this color is red, I get a signal. And that is the signal that we look for in LIGO. You can see as it's moving back and forth, as they become in phase, I now get a signal. This is what it looks like in scale. So this is LIGO Livingston, and from this corner station, where the laser, the interferometer, the photodetector are, out to the end test mass is 4 kilometers, 2.5 miles. This is the largest vacuum system, largest interferometer ever built, and this is what it looks like if you turn around and look back toward that corner station. Now, really, in the end, in order to make this measurement, what we're doing is we're bouncing laser light off of mirrors. Okay? This is a picture of the mirrors that we use. 35 centimeters in diameter, 15 centimeters thick, the purest, most high-quality glass available on the Earth, and it is polished to atom accuracy. Okay? Over a radius of curvature of 11 miles. It's a very, very slight curvature to it. Okay? And everything about being able to detect the gravitational wave is due to how the light actually reflects off of this mirror. The interesting thing is that although the arm cavities are 4 kilometers long, we have to be able to sense the length difference to 1/10,000th of the diameter of a proton. Let me give you a sense. This is an atom, and we have to 10 to the minus 10 meters, we have to go down 5 orders of magnitude to finally get to the proton at the center of the hydrogen atom, and then down further several orders of magnitude until this is just the edge of the proton that we're imagining moving back and forth. And this was the amplitude of the gravitational wave signal that we saw in September 2015. That is our most difficult challenge going forward, is to be able to do better, because we actually have to do, in the end, about a factor of 10 better than that. And that's what we work on here at HWS. In our lab down here is some of the students who have worked for me over time, is we actually have to work on the difficult problem of what to do about the coatings on that surface, because that is where the problem lies. This is, for those of you in the sciences may be easily able to interpret this, this is our noise curve and our sensitivity. And this is what we call our sensitivity bucket right in the center. This is where we like to measure gravitational waves. This is where we're sensitive to them, right in the audio band. This is where we will see, have seen, binary black hole systems, binary neutron star systems. And this is where the leading noise source is the noise source that we work on here, along with other institutions around the world. And we have to do better. This is the plan over the next few years, to take this curve that we have, and it will get better because we have found a way to get past the standard quantum limit. Everybody may have heard of Heisenberg's uncertainty principle in quantum mechanics. We found a way to beat it. And once we get past the quantum limit, we also then have to bring down the coating thermal noise. That is a task that is left for us to hopefully achieve only over the next 3 to 4 years. So we've got a lot of work ahead of us. Now, that is the particular noise source that we work on, but as you may know, we have a collaboration that at the time of our first detection of gravitational waves was around 1,000 people, and we've grown by a few hundred since then. These are images of the seals of all of the institutions that are working together. Each of them has a very challenging problem that they're all working toward, and it requires the cooperation of all of us in order to make this measurement. For a long time, since we turned on the original LIGO in the early 2000s, we heard nothing in our interferometer but noise. Now, I have to say that while what we are detecting is not sound waves, those waves map well to the audible frequencies. So we can essentially hear and listen for gravitational waves. And for most of our career, we've listened to this. Just static. And then, on September 14th, 2015, we were finally able to hear our first detection. Okay, so it may be a little bit hard even to hear that first detection. So here I'm going to have it queued up with a visual. So this is going to give it to you both in the time series and what we would call the time frequency plot. You hear that little whoop, whoop? That is 2 black holes in spiraling together and then finally coalescing into a supermassive black hole. And in the process, with that particular combination of black holes, radiating directly 3 solar masses of energy into gravitational wave radiation. That's the direct conversion of the mass of 3 suns, so 6 times 10 to the 30 kilograms, into radiation, gravitational wave radiation. That is more energy in gravitational radiation than is produced by all the stars in the universe during that brief period of time. So, the other thing that was amazing about that first signal is how well you could just see it clearly above the noise. And since then, we have made our living out of detecting other black hole binaries. So this is, I don't know if you can see it very well because the lights in front are a little bit high, but this is an artist image of what it looks like for 2 black holes to warp space-time and then come together. We have now measured 4 observations of binary black hole systems. This is the last one, announced only on the 27th of September, occurring on August 14th of this year, where a black hole of 25 and another black hole of 31 solar masses came together at about 1.8 billion light years away from us. And in the process, also with this one, to rounding error, lost about 3 solar masses of energy as they did it. So now, at this point, we've seen 4 sets of binary black holes. Here was the first one in September 2015, then in Boxing Day of that same year, then in January of 2017, and again just in August of this year. And here you can see the range of these masses. I want to point out that astronomers had not been predicting that this type of solar mass black hole would be existing. We knew of supermassive black holes at the center of galaxies. We knew of smaller mass black holes. But this population of tens of solar mass black hole is not something anyone expected for us to see, and yet we've been seeing them. I mentioned that we have to do better. Why? Because we're only probing out to orders of 3 billion light years, but the whole observable universe is 14 billion light years. We have to make another 10 times sensitivity improvement. We've got a lot of work to do. Fortunately, another big benefit of this most latest discovery is that this is a slide I showed when we did the previous announcement, but here Virgo has turned on. So in addition to our 2 observatories in the US at Hanford and Livingston, we now have our collaborators outside of Pisa in Italy who have a sister observatory that's a little bit smaller than ours, but has just come online with similar sensitivity, and it's done something amazing. Which is that before, when we looked out and we tried to pin down where this signal was coming from, we had a difficult time because we only had 2 points of reference. So here are our previous observations of our 4 black holes. And now this last one that we detected in August, because we have a 3rd detector, allows us to now pinpoint down the area of the sky from which it is emanating, and we see a 10 times reduction in area. That's key, because now we can turn to our partners in optical astronomy. And in the presentation you're going to see going forward, should we segue over? Yeah. Okay. This is key to what we're doing. All right, now we're going to segue over to the National Press Club.
President and Deputy U.S. Chief Technology Officer, and Federico Farini, Director of the European Gravitational Observatory. Representing the National Science Board is Maria Zuber. We're delighted you all could join us for this event. In February 2016, we announced the first ever detection of gravitational waves, ripples in space-time, caused by the merger of two black holes in a binary system 1.3 billion light-years away. The detection, made by the National Science Foundation-supported Laser Interferometer Gravitational Wave Observatory, or LIGO, confirmed a major prediction of Albert Einstein's 1915 theory of general relativity and marked the beginning of a new field, gravitational wave astronomy. It also came decades after NSF and the National Science Board approved initial funding to Caltech and MIT to construct and operate LIGO. LIGO is an instrument so sensitive it can detect the smallest ripple in space-time, lasting only a fraction of a second. Gravitational waves can only be caused by the most spectacular cosmic events, as when one black hole collides with another. Following that first detection, scientists confirmed a few more detections of gravitational waves caused by colliding black holes, the most recent of which was in conjunction with Virgo. There is, of course, another event we were keen to detect. Today, we're thrilled to announce that scientists have detected gravitational waves coming from the collision of two neutron stars, the smallest and densest stars. This event occurred 130 million light years from Earth in a galaxy far away. The LIGO detectors first picked up the signal. When Virgo did not see a signal of similar magnitude, it was clear the event was close to one of Virgo's blind spots. This enabled scientists to localize the potential origin of the signal more precisely, allowing ground and space-based telescopes, some 70 in all, to turn their attention there as well. What makes this discovery even more exciting is that scientists were also able to detect light, electromagnetic waves, from the collision. The very same cosmic event seen for the first time through multiple messengers, gravitational waves and electromagnetic waves. As an astrophysicist, and someone whose passion for physics was first ignited by a television program on neutron stars, it's especially exciting for me to report on this rare event. Already it is transforming our understanding of the universe with a fresh narrative of the physics of stars in their death throes. The scientists who conceived of building LIGO and were primary drivers, Kip Thorne and Barry Barish of Caltech and Rainer Weiss of MIT, are receiving the 2017 Nobel Prize in Physics. Their vision and perseverance and NSF support made this discovery possible. This is what NSF does. We invest in high-risk, high-reward research that produces the discoveries that transform our world and advance the frontiers of knowledge. The benefits of these discoveries are not confined to the scientific community, but extend throughout the world, as discoveries from basic research coupled with novel engineering often do. Today's announcement should excite the scientists and non-scientists. It's a measure of what is possible when we have the courage to push beyond the limits of our knowledge and pursue answers to big questions. At this point, let me turn the program over to Dr. David Reitze. When we first announced the first gravitational wave discovery a year ago, David captured the excitement of the moment when he declared, "We did it." Well, Dave, we did it again.
Thank you, Dr. Cordova. Good morning, ladies and gentlemen. We have, for the first time, seen both gravitational waves and light from the collision of two dense dead stars called neutron stars. However, to do it this time, we joined forces with thousands of astronomers and many, many observatories. So we did it again, but this time we all did it. Let me start by telling you what we saw. The LIGO Virgo network discovered two neutron stars colliding together. So LIGO is the LIGO Hanford and Livingston Observatory here in the United States. Virgo just started operating in August of this year, and we saw a signal at 8:41 a.m. Eastern Time on August 17th. The signal was much different from the black holes that we had detected before. It was much longer. And we analyzed this signal, and what we found was that it was a neutron star, approximately 1.6 solar masses, colliding with a second neutron star, approximately 1.1 solar masses, about 130 million years ago, 100 million, 30 million light years away. So this graphic that you're seeing here is just the brief second where they collided. Now, this is a source that we always thought we would saw. Neutron star systems, binary neutron star systems have been predicted for decades, and we knew that we would see them. For me, what makes this event so amazing is what came next. The emission of light across the entire electromagnetic spectrum, revealed to us by a campaign involving 70 observatories, including 7 space-based observatories and every continent on the planet. So if you look at the graphic carefully that I'm showing, you'll even see there's a dot in Antarctica. So this is quite dramatic. This is an amazing, amazing discovery. And it was made possible by the fact that LIGO and Virgo, operating together, can identify the place in the sky where this event came from. It came from the southern hemisphere. It came from the Hydra constellation. So let me tell you a little bit about neutron stars. Neutron stars are very different from black holes. Now, they're produced from supernova, the explosion of massive stars. They're approximately 1 to 2 times the mass of the star. However, they're made up of pure neutrons. And the density of the neutrons in the neutron star is much, much greater than atomic nuclei, actually about a factor of 3 times greater. So consequently, they're very compact. Neutron stars are about 20 to 25 kilometers in diameter, and you can see in this graphic that I'm showing you the Bay Area and San Francisco. That peninsula is San Francisco. So what you're seeing there, to get a sense of this, is 1.5, 1.6 solar masses packed into a very, very compact region. So, all right, what does this really tell us? Well, astronomers have thought for a long time that the collisions of these neutron stars produce heavy elements, and there's been hints of that in other astronomical observations. But this result provides definitive evidence for first time that elements such as platinum, gold, uranium are actually produced in these collisions. So I'm going to take out this is my great-grandfather's gold watch. It's about 100 years old. The gold in this watch was very likely produced in the collision of 2 neutron stars approximately billions of years ago. We don't know exactly when. So this is really an amazing discovery. You're going to hear today from the physicists and astronomers who participated in this remarkable discovery. In fact, the scientific story is so rich that it takes 2 panels to tell it. So you're going to hear from 2 different panels today. For me, the story is actually, the big story is the fact that we're now using this new tool called gravitational wave astronomy, and we're combining it with traditional and very powerful electromagnetic astronomy to study the most powerful events and violent events in the universe. All right, so the analogy I'll give you is this is the first time the cosmos has provided for us what I would call a talking movie. We've moved from the era of silent movies to talking movies. In this case, the audio soundtrack comes from the chirp of the neutron stars as they are inspiraling, as they're orbiting together and colliding. And the video is basically the light that we see after the collision. Right, so before I step down, I actually want to also acknowledge that this kind of science does not happen without sustained support from agencies, and in our case, it's the National Science Foundation, which has steadfastly funded us for over 3 decades. And this is, again, another example of what I would call high-risk, high-reward science, where NSF swung for the fences scientifically back in the 80s, and we've yet again hit a home run. So I'm now going to call my friend and colleague David Shoemaker to the podium, and he's going to tell you a little bit about gravitational waves and how we detect them.
Thank you, Dave. I'm an instrument builder, and so I want to tell you a little bit about how these instruments actually can function. But first, let me say a bit about gravitational waves. Let's imagine you have a wave that's coming at you. The effect is to squeeze space along one axis and stretch it on the other, and then squeeze and pull in this direction. But space is incredibly stiff, and the result is that this event, some 130 million light years away, only made the smallest change you could imagine. If you had, for instance, a yardstick and the gravitational wave were to pass next to it, it would change length by less than a billionth of a trillionth of an inch. On the other hand, if you say, what's the change in distance to Alpha Centauri, some 4 light years away, it changed by the thickness of a human hair. So that's how small the effect is, and that's our measurement challenge. So one of the things, though, I just said is that you get a bigger effect if you go further away. The gravitational wave is a strain in space. It's like stretching a rubber band. And when you stretch a rubber band, Let me get to the right film here. Good, there we are. When you make a longer baseline measurement, you have a signal which is larger. And that's why LIGO and Virgo have arms which are miles long to boost up the signal to the point where it can actually be measured. But you still need some of the most sensitive devices that have ever been made to have a sensitivity that suffices to get a measurable signal. You also need, critically, hundreds and hundreds of people who can design and build and install and run these instruments, and then thousands of people around the world in the LIGO and Virgo collaborations who then can analyze the data and get something useful out of it. So now we're going to look at a simulation of an interferometer. We use interferometry. We compare the peaks and troughs in light waves that travel down the 2 arms and then back together again. Now, between the peaks of the light we use is about a billionth of an inch. But in fact, we can split that down by another factor of a billion by using very powerful lasers. Really, it's the quantum effects of light that limit how well we can do. And with that, we can actually get to a signal that is measurable when the gravitational wave passes and shifts those wavefronts by a tiny amount. So software is constantly scanning the data that comes out of this interferometer and matching against hundreds of thousands of templates. We're looking for a match between what we see in the wiggles in the data and these different waveforms. The first time we saw this signal, it was in the Hanford detector up in Washington. That was where the signal was the cleanest and easiest to see. About that same time, though, we saw a gamma ray alert. Julie McHenry will tell you a bit more about this in just a minute. And that is a thing that made us realize that we were at a watershed moment for multi-messenger astronomy. We quickly put together a sky map that was based on the signals that we saw in Hanford, Livingston, and Virgo to form an idea of where this was in the sky and to give the astronomers a sense of where to look. That morning, I was talking with Laura Caudenanti about some rather boring bureaucratic matters that we're spokesperson and deputy spokesperson of the collaboration, and we were trying to figure out how we could get the collaboration to change its way of thinking for the post-detection era, when suddenly the phone alerts went off, and we immediately jumped over to the voice channel where all of the experts had gathered to try and understand where we were, and we shared in the joy and excitement of that moment. Now, while earlier detections of the black holes that we'd made, you can see it in the upper left-hand corner of this graphic, of this simulation, only lasted for us a couple of seconds or much less, this neutron star in spiral lasted for over a minute. And that's because these are lighter masses than the ones we've seen before. They're only about the mass of the sun, or 2 times the mass of the sun. And as a consequence, their frequencies are shifted up into a region which matches better the most optimal place in our instrument response function. And the result is that we can see the system for some 1,500 complete cycles of these 2 objects around each other. And it gives us a chance to get a very precise measure of the parameters of the system. But you have to imagine this. We've got these 2 objects, each one about the mass of the sun, but collapsed down to objects that are only 10 or 15 miles across, spinning around at close to the speed of light. That's a simulation, but that's what it sounds like also in the data. Spinning around at close to the speed of light so that they are eventually mixed together to make a single final object. It's an absolutely astonishing idea. We'll hear more about the fireworks that took place after the two fell together in terms of all the electromagnetic follow-up. Well, the resulting object and its electromagnetic radiation really is a treasure trove of information and is going to lead, I think, for months or perhaps even years of study to understand better exactly what happened with these two objects. We don't actually know what happened to the objects at the end. We don't know whether it's a black hole or a neutron star, or perhaps something else. Some of the panelists later on will give some of the ideas of the evidence that they have for one choice or the other. Maybe some continued observation will lead to a really complete and final answer. Well, with that, I'd like to turn the podium over to Jo Vantenbrand. He's my opposite number in the Virgo collaboration, and he'll talk a bit about how we were able to point the astronomers to the right place in the sky. Jo.
Thank you, David. So the brand new European Virgo detector joined LIGO in the second observation run in the month of August. We joined for 3.5 weeks, and it were the most spectacular weeks. It went beyond all our most optimistic expectations. So now we have a free detector network, and this allows us to localize the sources much better. So the gravitational wave first arrived in the Virgo detector. And then 22 milliseconds later, it was seen in the detector, LIGO's detector in Louisiana, and another 3 milliseconds later, it arrived in the Hanford detector in the state of Washington. So this allowed LIGO and Virgo to pinpoint the source of the signals to about 30 square degrees in the Hydra constellation. And this is by far the most precise sky localization of all gravitational wave events so far. So to get an impression about that, you see here the first binary black hole events detected by the two LIGO detectors only. And you see that the average sky localization, so projected on the sphere of the Earth, is about 1,000 square degrees. So now if you include Virgo, you get a global free detector network, and the sky localization dramatically improves. So this event was relatively close by. The SNR was the highest of all gravitational waves detected so far. So you might be surprised, why is the signal so low in Virgo? So now every detector has an antenna pattern, and that is shown on the slide there. And there are places in the sky, actually 4 spots indicated in dark, where the detectors are not very sensitive. Now you see also in the star where the source of gravitational waves was, and it was near a bright spot, near the most sensitive region of LIGO. On the other hand, in Virgo, the signal was hiding near a blind spot, and that explains why the signal was low. Still, the information in Virgo was sufficient to do the localization, and this allowed the follow-up studies to proceed. So with LIGO and Virgo, we could look at the source and identify these two neutron stars, and this was followed by a flash of high-energy radiation seen first by Fermi, and later also by Integral, and you see the common sky position indicated by the electromagnetic signals. So then you can look at the LIGO information. This is this circle on the sky. And combining that with Virgo, you see now that the gravitational waves point at the same sky location as you independently find from the Gamma-ray burst observatories. Now, if you look into that, then this region contains about billions of stars, about 50 galaxies. And it took a little bit over 10 hours for the astronomers to find the optical counterpart and the galaxy. So all this, I think, is an unprecedented demonstration of a global effort involving thousands of research universities and institutes and scientists, and looking all at the same single astrophysical phenomenon. With gravitational waves from LIGO and Virgo, we could see the source in fantastic detail. and then follow up by this flash of high-energy radiation detected by the satellites. And then subsequently, the source was studied in more detail by thousands of astronomers. The importance, the role of NSF was already pointed out, but I also would like to add that the realization of Virgo was possible because of the continued funding by both CNRS in France and by INFN in Italy, and later in the last decade followed by the Netherlands, by Hungary, Poland, and Spain. So we did a lot of science, from fundamental physics to astronomy to astrophysics. We actually started right now on cosmology and nuclear physics. And I think this is a demonstration of what mankind can achieve if we put our minds to it and if we collaborate. So I think it's the start of a beautiful new field in science. And with that, I would like to hand over to Judy, who will talk about how Fermi saw the high-energy radiation. Please.
Thank you. Gammarays, the highest energy form of light, kicked off the light show. The gamma-ray burst monitor on the Fermi Gamma-ray Space Telescope views the entire sky that is not blocked by the Earth. Around twice a day, we detect flashes of gamma rays. Flashes of gamma rays from thunderstorms, gamma rays from flares from our sun, outbursts of gamma rays from exotic stars in our galaxy. And important for the discussion here, a few hundred times a year, we see a brief flash of gamma rays from a gamma ray burst, a huge explosion in galaxies far away. August 17th started off as a perfectly normal morning for Fermi. We had breakfast. A gamma ray burst was detected, which by itself is not particularly surprising because we see quite a few of them. We saw a brief flash of gamma rays lasting just under 2 seconds. Half an hour later, we got an email from a colleague at Marshall Space Flight Center who works on both Fermi and LIGO saying, "Wake up!" in an email, which didn't actually wake us up, but okay. This burst has an interesting friend. And a few minutes later, we got a formal report from the LIGO and Virgo teams saying that they had detected a gravitational wave signal consistent with merging neutron stars just 1.7 seconds before the gamma ray burst detected by Fermi. And here I show the gravitational wave strain plot seen by LIGO. Half an hour later, we received another report from scientists working on Integral, a gamma ray observatory operated by the European Space Agency, who said that they had also seen the gamma ray burst. And with this started the most exciting morning of the 9-year Fermi mission. And the reason that this was so exciting is that there had been a long-held prediction that gamma ray bursts, these enormous explosions, that some of them, the ones that are short in duration, were powered by neutron star mergers. So within the first few minutes of getting this email, we realized that we had actually confirmed this prediction. So what do we think is going on? You've got two neutron stars that are spiraling around each other, spiraling closer and closer together as they lose energy by radiating gravitational waves. When they finally merge, they produce a huge energy release that powers jets that expand out into the material between the stars. We believe the gamma rays are produced in these jets. So this is great. We've solved a long-standing problem. But we're intrigued. In the Fermi detector, this looked like a perfectly normal gamma ray burst, just like any other short duration gamma ray burst that we see. But we knew from the gravitational waves that this burst was located more than 10 times closer than any other short burst with a measured distance. So it should have appeared very bright. So what's going on? One possibility is that we're not viewing this gamma ray burst down the barrel of the jet in the way that we usually do, but perhaps we're viewing it at an angle. Just as if you have a flashlight that dazzles you when you look straight at it, but if you're looking at an angle, it appears dimmer. With these observations, we're not just learning what happens when neutron stars collide. We're also learning something fundamental about the nature of the universe. The gravitational waves and the gamma rays traveled across the universe together for 130 million years and arrived within 2 seconds of one another. That's telling us that the gamma rays and the gravitational waves are both moving at the same speed, at the speed of light, as predicted by Einstein. So yet again, Einstein passes another test. So the story didn't stop there. The observations continued, revealing new and exciting features that the next speaker, Marika Branchesi, will tell you about. Thank you.
So Julie told you what Fermi saw in the sky, and I want to tell you what is the following story. So around 9 a.m. Eastern Time, about 90 group of astronomers around the world were alerted about the presence of the discovery of a gravitational wave signal coming from the coalescence of 2 neutron stars, 2 seconds before the gamma ray burst. A key moment happened about 4 hours later, when we sent the sky localization of the gravitational wave signal obtained with the LIGO and Virgo observatory. The sky localization was pretty good, and this source was close with respect to the other detected before. So a small universe and a nearby universe to be observed, a part of the universe where we know the galaxy. And at this point, all the observatory around the world start to look at the sky. And in particular, this source was located in the southern hemisphere, an ideal place for the Chilean telescope to look at that. And the Chilean telescope started to look at our sky localization at the twilight, and the first light escape has appeared as a very new bright object in one of these galaxies, NGC 4993, that is at the same distance of the gravitational wave source. We observed this object in all its colors, starting from gamma ray, then the blue ultraviolet light that fade rapidly and evolve in a red infrared object over a week. And then we discover also an X-ray emission and the radio emission after 9 days and after 16 days. This amazing discovery comes from a collaborative effort of different communities and 70 observatories that, including 100 instruments, they look at the same position of the sky for weeks. Each night observation brought a new piece to the puzzle to understand the neutron star and the engine that power light and sound. This is the start of the multi-messenger astronomy that allows us to hear the sound of the gravitational wave and at the same time to see the colors from the light. And the multi-messenger astronomy use different waves and different particles to observe the sky, also neutrinos. This time we didn't detect neutrinos, but we hope to add this messenger in our future observation. So the light in some band are expected also after years after the merger. But all is decided in a very small amount of time when the 2 neutron stars dance around each other, became very, very close, about 10 milliseconds before the merger. They start to feel tidal effect, tidal forces, and up to a few seconds after the merger, a matter is violently ejected in the interstellar medium. And this matter is the perfect side where heavy elements can form. And the radioactive decay of this element powered the light that we saw in the blue, red, and near infrared. And this was predicted by the theories before. And we obtain amazing data, and some of them are, for example, from the telescope, the ESO VLT shooter, Gemini, and the Hubble Space Telescope. And now I show you this data taken by the VLTX shooter, here you can see a brightness decrease very, very rapid from the first to the second day. And from the third day, you can see in the spectra some broad feature that evolve. And these broad feature are the result of broad line blended together coming from this heavy element. So when the light escapes the matter, the universe is enriched by heavy element, and heavy element including also gold and platinum. So this, for the first time, we have observation that a large amount of these elements heavier than iron, form in this type of merger. And we learn a lot about neutron stars and their life in the galaxy, and Vicky Calogera will talk about this in the next talk.
Thank you, Marika. Ooh, fast. There we are. So what I would like to do in the next few minutes is tell you a little bit about the history of two neutron stars in a pair, and also the history of this particular discovery. So this is the first time that we hear the death spiral of two neutron stars, and we also see the fireworks that came from the final merger. But for decades, thanks to observations, astronomy observations in the radio wavelengths of light, we have known that pairs of neutron stars exist. It turns out that neutron stars are not just highly compact, as Dave Wrightsey already told us, but they are also acting as cosmic radio lighthouses. So they emit radio jets, and when those radio jets, as the neutron stars are spinning around their own axis, when those jets are crossing our radio telescopes here on the Earth, then we see radio pulses. So back in the late 60s, Jocelyn Bell Burnell and Tony Hewish discovered neutron stars as radio pulsating stars, pulsars, in our own galaxy. And we now know that many neutron stars actually appear as pulsars. And just a few years later, in 1974, Russell Hulse and Joe Taylor discovered the first ever actual pair of two neutron stars. One of them was actually observed as a pulsar. The other might be a pulsar, but for sure we knew it was a neutron star. And they were found in an orbit that radio observations allowed us to tell that the orbit was not stable, but the orbit was actually a spiral-in orbit. And the spiral-in was happening as fast as Einstein predicted it should happen, based on the emission of radiation of gravitational waves. It was the observation of this system that was discovered by Hulse and Taylor that actually provided the very first firm evidence that gravitational waves existed in nature. And it was this system that made gravitational wave astronomy a dream worth pursuing. In the Hulse-Taylor pulsar, we know that the two neutron stars are actually very far away from one another. They are over 1 million miles apart, 5 times the distance between the Earth and the Moon. And they will not merge for another 300 million years. But this discovery we are announcing today, when the two neutron stars entered and we could hear them with LIGO and Virgo, they were just 200 miles apart. And of course, more than about 100 seconds later, they merged. However, before their final 100 seconds, they had a long life together as a pair. And it turns out that before the second neutron star was formed in the system, it was the system, the progenitor of that pair of neutron stars, had a long, quiet life in its home galaxy. So it was going around its business, orbiting its own galaxy in a quiet orbit, the green orbit. It was green, the orbit in the galaxy, until the second neutron star was formed, and the system was kicked in the galaxy in the last phase of its life, And it was kicked in an orbit that allowed it to visit all kinds of neighborhoods in the galaxy. It went on a vacation at the last part of its life, touring all around, having new experiences all around the galaxy before the two neutron stars found their death together as a pair. And we can tell all of this by having the information from gravitational waves and electromagnetic waves. Now, what you see in the movie is that there's lots of little dots there. We haven't discovered lots of little mergers. We have seen one merger. But when we do our computer simulations, we cannot isolate a single orbit in the galaxy. We have a collection of orbits that are likely the history of this system in terms of its motion in the galaxy. So overall, I would like to highlight, as other speakers have done, that what's amazing with this discovery is that theoretically, all of this that was observed on August 17th was actually predicted. So over a century ago, Einstein predicted that two orbiting objects will emit gravitational waves as they spiral in. And astrophysicists predicted that as the two compact objects, especially neutron stars, collide, they should emit gamma rays in jets. And a cascade of light across the whole electromagnetic spectrum was predicted, and the production of heavy elements that might include gold and platinum should be produced. So it's amazing to think that in one day, in a few hours and the weeks that followed, all these predictions were confirmed. So we solved a lot of mysteries, but at the same time, we also opened up a few questions. As Julie said, not everything fits perfectly in the puzzle. So we're opening up a new set of questions. We're hoping that future observations that for sure are going to happen, both with LIGO Virgo, but also with our electromagnetic partners, are going to answer a lot of those questions. So the future for multi-messenger astronomy is definitely bright, and I might say golden bright. Thank you.
All right. Thank you to all our panelists, and we're now open for questions. Yes.
Seth Borenstein, the Associated Press. As Vicki just said, this was most of the things from the heavy elements, the art process, to the Hubble constant and gamma rays were all theorized already and confirmed. What was the most surprising things you found, the new puzzles? What didn't fit that you now have to go and find as opposed to what you confirmed?
So one thing was mentioned by Julie. Maybe she will elaborate. I mean, the faintness of the gamma rays, even though the source we know from the gravitational waves is so close by, is definitely a mystery. And I would say the delay probably in the X-rays might be a connected mystery. And you're going to hear a lot more about this from the second panel. And others may have something more to add.
Right. Another question, please?
Yeah, so given the light activity
Could you
that's...
identify yourself, please?
Oh, Yun Yu from Inside Science. So given the light activity that's predicted by the model during the neutron star merger, is there anything to gain, perhaps to implement some kind of automated system so that all the telescopes can point before even humans are aware of the event?
Yeah, that's Marika. Why don't you take that?
Yes, it's very important because, okay, this object was close and the region of the sky was small, and we expect more distant sources. We expect also to have a bit larger region of the sky to observe. So it's extremely important to have a robotic telescope that look at the sky continuously, and also automatic system to analyze the data and to remove all the contaminants, because we have transient objects in the sky, objects that appear and disappear, and some of them are very similar to the counterpart of gravitational wave signal. And so this is an extremely important part of this discovery.
Right, question here.
Hi, Sarah Kaplan from the Washington Post. You all have talked a lot about the significance of multi-messenger astronomy and how that's a big revolution. Can you talk about are there specific astrophysics questions that we're going to be able to answer now that we have these two messengers, particularly ones that readers who are maybe not physicists will be able to understand?
Let me try and take a crack at that. So another source that we would love to see, and that we would not only see in light and gravitational waves, but also in neutrinos, is a supernova explosion. All right. The problem with the supernova explosion is that we have to get really lucky, because they're very weak emitters. We can't see them outside our galaxy. They produce, tiny, tiny fractions of mass converted into gravitational wave energy. So they happen about once every 50 years. But certainly in the future, when we're running, we're going to be looking for that. And there are going to be more gravitational wave detectors that are coming online in the next 2 to 5 years, that when some of the detectors are down, some of them will still be running. So we'll hopefully still be able to capture them.
Can I add something to that, David? The other thing, if we collect more of these sources, these binary neutron stars, as we did so far, then we also can start getting into cosmology. So, for example, right now, already with this first event, we get sensitivity to the Hubble constant. And given our analysis, if we build up more of these events, we get more and more a handle on cosmological questions.
Right. Any other questions? All right, then we'll take a short break. I'm sorry, is there?
We have a number of questions from the...
Oh, okay, Lisa? Yeah.
Yes,
yeah.
thank you.
So this is questions from the webcast.
From the webcast, that's right. Rashmi Shivni asks, scientists saw signatures of recently synthesized heavy metals like gold and platinum, which basically solve the long mystery of where half of all the elements heavier than iron are produced. So, can we predict the frequency of these neutron star mergers events based on the proportion of heavy elements we see in the universe?
Try that one. So, actually, we can indeed attempt to do that. And one of the publications that is being released from the LIGO Virgo collaboration is attempting to do this kind of calculation. And I am sure I haven't seen all the publications that are being released today from our electromagnetic partners, so other colleagues might have attempted to answer that question. But I will say the following, that the question of how often these mergers happen is much better answered by the observation itself in gravitational waves. So not from the calculation of what the quantity of these heavy elements we have. Because we have a high uncertainty for how much gold or platinum we're forming in each event. So the uncertainty associated with that is quite high. Instead, we know how long LIGO and Virgo have operated so far. And we know that we have detected one event, and we can calculate a rather tight constraint relatively to previous constraints. We have now a tighter constraint on how often these mergers happen. And just to give you an idea, these are very rare events. So with this one event, we can tell that in a galaxy like the Milky Way, our own galaxy, maybe they're happening somewhere between, very rough numbers, between 30 and 500 events in our galaxy per million years, okay? So don't hold your breath about a merger like this in our galaxy. The only way we could see one in a couple of years of LIGO operations, for example, is because LIGO and Virgo are listening to millions of galaxies. Tens of millions of galaxies. And this is why we can get one in a couple of years, roughly speaking.
Okay, but it's a very good question, and the next panel may also shed some light on that. And I think it's going to keep theorists very busy working on that kind of question.
We have some more questions.
All right, in the interest of time, we're actually going to switch back a second. And I do have other slides, but I wanted to first open it up to questions to see if you have questions about what you've heard today, either from my first presentation or from the panel discussion. And then if not, I can switch over to other slides. So first, let me open it up to questions to see if anybody has any questions this morning.
I'll wait.
Yeah, give Shivam a chance first.
So I guess I just never realized that gravitational waves moved at the speed of light, and was that discovered with this?
It was
observation,
confirmed.
It was confirmed.
It was confirmed with this observation. So as part of the general theory of relativity, Einstein assumed that gravitational waves move at the speed of light. That's the only way that that theory is self-consistent. But it has never been measured. And this provided a wonderful opportunity for us to do that, because now you have a source that's 130 million light years away. And because neutron stars are so small, the difference between the release of the gamma rays and the release of the gravitational waves should also be small. And those two signals were detected only 2 seconds apart. So if you do that calculation, and we conjectured different scenarios for either the early production of gamma rays that might be slowed down given the slight index of refraction in space. We tried to find the widest reasonable range of separation of those two. But what we found is that the variation between the speed of gravitational waves and the speed of light is only a few parts in 10 to the 15. So this is extremely good measurement that gravitational waves travel the speed of light. And all the theorists are, whew, great.
Never worried. Never worried.
Yeah, okay. Well, the other thing I should say, which is a wonderful confirmation, is that the waveforms that are expected for neutron stars are very well determined. These are much smaller masses, and so unlike the coalescence of black holes, where you have a very short, even sub-second waveform that you now have to match up, this is something that was ringing for tens of seconds. So over 1,000, I think David said 1,500. I saw estimates as high as 3,000 distinct oscillations that we could then compare and look at the rate at which, under a chirp, the amplitude is increasing with frequency. That's what gives us the very accurate determination of their masses and therefore their distances. But that waveform is extremely well matched by general relativity. So Einstein wins again.
All right, I actually have a question, if I may. Okay. So in your discussion, in the discussion from Washington, they were still talking about EM and gravitational waves as though they are two separate creatures. Now, of course, one of Einstein's conundrums was EM and gravity behaving differently in some important ways. Do these discoveries bring us any closer to understanding the relationship between EM and gravity in a unified theory of physics?
In short, no. But I mean, there's two separate sources. The gravitational wave is produced by the inspiraling of the neutron stars warping space-time at higher and higher curvature in an oscillating quadrupole, okay? Whereas the production of the gamma ray burst is due to, as these spinning neutron stars come together, they're forming a jet of material, and there's a lot of what we would call R production of nucleosynthesis happening there, and a copious source of gamma rays, which you would expect from a nuclear reaction. So they're totally, I mean, they are coming as one event, but the sources of the two are quite different.
Why jets as opposed to some kind of spherical emission?
Okay, so as was alluded to in the press conference, the exact remnant and the exact formation isn't well determined yet. There's still a lot of observations and a lot of theories that have to be compared to those observations. So the theorists have been putting together movies, and some of them show more of a spherical explosion, but you do have this phenomenon that when you have objects that are rapidly in-spiraling, and you see this also with even spinning objects like neutron stars, pulsars, for example, they allow jets along the axis of their rotation, right?
That's the direction of the jet.
That's correct.
Is the axis.
Right. You see this also in radioactive galaxies. It's just a phenomenon that when that matter is coming together, one of the possible trajectory for the particles is to stream out along the axes. Don, you had a question?
So first of all, cool stuff. Should mention that the speed of, I do have a question, the speed of light, there were indirect confirmations that speed of gravity, speed of light were the same from Carlip's, a paper by Carlip, I think 1999, from the lack of aberration. It's a really cool paper. But this is the first, obviously, direct measurement. So the triggers, you indicate a time for the event. So I don't know if you know how the gamma ray burst is timed, but you've got somewhere between 1,500 and 3,000 cycles for about a minute. What's the time indication that you pick for the time of the event for that 1.7 second gap?
For our timing or their timing?
Well, for your timing, and if you know for their timing.
Okay, so let me go forward.
Where in that sequence is the time?
Okay, let me actually go forward a couple of slides here because I have there's a few movies, but I don't want to start playing them. So let me... I
mean, if you'd rather talk about it later, that's fine too.
No, this is fine. Let me shift forward to here. Yes. Okay, good. So you can see here, these are the time frequency plots for Hanford and for Livingston. And this podium is very awkward for me to bend over here and show this to you. But Livingston right now, for various reasons I can go into later, is a little bit more sensitive than Hanford. So you can start to see the time frequency plot. Here is the signal coming up. And then this then escalates very, very sharply. And that is what we consider the time of the event. That's the coalescence. And afterward, you don't see very much gravitational wave signal, okay?
Yeah.
And you can see it, but you can also hear it. And let me see if I can, oops, no, not that one. Okay. All right, let me try and play these. This is what we heard directly. And if you like listening to static, you can actually start to pick out the signal already. Okay, now this is it without the static. I don't know if you can give me any more volume. Hello, hello. Here it is. Hear it? There it is. Okay. So that's what gives us the timing.
Okay, so the timing is not the time of that you first see something, but the time of the coalescence.
That's right.
Okay.
That's right.
Yeah.
That's right.
And
you I should say in simulations of this, and we can detect this in the waveform as well, is that you're also getting tidal effects.
Right.
So the neutron stars themselves are distorting as they're getting closer to each other, and that actually affects the waveform.
And one other quick question. So there were no neutrinos observed?
No.
I know.
Not expected either.
That's my question.
Given the source.
What's the, how close would they have to be for there to have been a detection, expected detection at Ice Cube or Antares or something? Do you know?
Certainly I would think within our galaxy, yes. Outside of our galaxy, I'm not sure where their cutoff point is.
Okay.
Okay. And then also, this provides an interesting phenomenon, right? Because the speed of the neutrinos should be different.
Right. Well, not the...
Yeah, slightly.
Well, not completely clear, but we'll talk about it later. I mean, there's some data from 1987A, right? It should be slightly less, but it's far away, so you might be able to pick it up.
Right.
But they also emerge...
1987A was much closer.
Oh, no, I understand.
Right.
Right. But they also emerge...
So I don't actually know what delta T should be. Right.
I don't know whether you would see them before you saw the light in any way. In a supernova, you do. And I just don't know what the processes are.
I don't think that they... Right, so what he's talking about is when all this nucleosynthesis is happening, you're also having copious production of neutrinos. With a supernova, it takes a little while for them to make it out. They're coming out, the light is coming out, and because the neutrinos pass through matter very quickly, you see that signal oftentimes before you see some of the light from the... Yeah. Okay, so depending upon the size of the object. And we don't have a good idea also yet of the amount of ejecta as opposed to, there's a possibility that there was a black hole formed, so we don't know how much matter might be in the black hole as opposed to ejected yet. So there's still a lot of science that remains. Shivam?
So you alluded to this earlier about how one of the biggest things coming forward is fine-tuning the mirrors, fine-tuning the coding and things like that. And you said the projected path is like 2 years from now, 4 years from now. Is it based on discoveries, things we know already, or it's like we're kind of hoping the process goes this way so we get this? We're hoping for results in a couple of years.
There was a lot of pressure on our research community before we detected gravitational waves because, as was mentioned, this was the biggest project that was ever funded by the NSF. And over the years, there have been a lot of detractors who have done everything from lobby the government not to fund us to people who basically, advised a lot of us personally that we were throwing our careers away if we ever wanted to go into this because you're never going to see gravitational waves. And literally, I think if we told NSF from the start that we would not see gravitational waves with initial LIGO, that we had to build advanced LIGO, but that we were building initial LIGO in order to learn enough about making large interferometers that we could then build advanced LIGO. And so while that initial detector was going on, we were, and including me, actively working to try and develop the science that was necessary in order to build the advanced detector. Okay, so those mirrors that I showed you a picture of were coded by a coding that me and a small group of other people developed and tested. That happened several years before Advanced LIGO went online. I think if we hadn't made a detection, we might be a dead project. Fortunately, that's not true. And now the reverse is happening, where people have been very excited, and the astronomy community was excited when we were just detecting black holes. Now I can say that the attitude within the astronomy community toward LIGO is euphoric. And hello, okay. And so that has done nothing but increased the expectation, the desire that we do something to increase our rates, because detecting a few things per year is considered not enough. And that's why there is now a lot of pressure on us to do whatever we can to up the rates. And the only way that we can do that is to increase our sensitivity. And the big roadblock, as I mentioned, we already have a way of getting around the quantum limit, which is pretty phenomenal.
Yeah, I was going to ask that question.
But the big thing standing in the way is the mirror coatings themselves, because the mirror, what sits on the surface of the mirror is basically where the rubber hits the road as far as determining where that mirror is positioned. And that coating and its mechanical qualities are things that no one else in the world is interested in. No one else cares to the accuracy that we do. And we have to do better in order for LIGO to be able to see further out into the universe. But let me say, any gain we make, there's a big bang for the buck. Because if we increase the quality in our mirror coatings by a factor of 2, we see a factor of 2 farther out, but the volume of space that we now see goes up by the cube, so we see a factor of 8 improvement in our count rate. And if we get a factor of 10, that's a factor of 1,000 in count rate. And now we're really sitting pretty as far as rates go. So there are a lot of people in the astronomy community in general, and I have 1,000 collaborators who are looking and saying, have you done it yet? Okay. You had another question about the quantum limit.
Yeah, so I'm about to run a quantum mechanics in like 7-8 minutes, and
Okay.
I was kind of taught that.
So Heisenberg's uncertainty principle tells you that there is a limit to the uncertainty in position and momentum, or you can think about it in energy and time. But let's talk about position and momentum. And so we can't get around that, okay? But it's the product. It's the product that is the limit. So there are places within our noise spectrum where we care less about the momentum and more about the position. And so we're actually able to tune our light at given frequencies so that we are then have more resolution in position and less in momentum.
So you're not really getting around it. You're just
You're getting around what's called the standard quantum limit,
okay.
which is the product of untuned light. But we're actually able to tune the light so that it's called squeezing. We squeeze the uncertainty so that the total area remains the same, but that we have, and it's at low frequencies we care less about the momentum, and at high frequencies we care less about the position. Are there any other questions? I do have some movies if you're interested in movies. I'm not sure when we're calling a close to this. I guess some people have already spoken with their feet. I just have 2 movies to help you visualize this, and then maybe we'll call it an afternoon or a morning. So this one is made by NASA. Hopefully this, hello. Let's try this again. The NASA movie's not playing. This is one that's made by our friends in Australia. So this movie mentions one important discovery that not many people have touched on this morning, which is that with gravitational waves, we can measure the distance to the objects, okay, quite accurately and directly. This is a big benefit for astronomy because previously when we were trying to understand both the distance to objects and especially distant objects, and trying to understand how much the universe was expanding, we had to do these distance measurements using a distance ladder. So we would measure close objects like variable stars and then determine by the period of variable stars in distant objects how far away these objects might be. But with gravitational waves, we can make a direct distance measurement. And we can look at the spectra of these galaxies, and we have to take the velocity of the local group of galaxies, and we have now a direct measurement of the Hubble constant. And so this, as we expand our range through the universe, we can now have a direct measurement of the Hubble constant going out with distance. Now, right now, our measure of the Hubble constant has such high uncertainty associated with it that it doesn't do anything to limit what is already known about the Hubble constant. But the fact is it's a new technique, and as we get better and better and can look farther and farther out into the universe, then we should be able to make a direct measurement even out to great distances. Don?
You're not doing better than type 1a supernova, are you?
No.
Okay.
Right. We.
Don't I just want to make sure that I understand.
No. Right. So we've only made one measurement, and that was 70 kilometers per second per megaparsec, and the uncertainty is plus 12 and minus 8. So right now, our uncertainties encompass all previous measurements. Not all previous measurements, but the two leading schools of thought as to what the Hubble constant might be. But the important thing is that, okay, that's where we're starting. And in going forward, this would allow us the opportunity to make these measurements, especially when we start to get to more distant objects. So after we improve things by a factor of 10 or more. Was that a question, Shivam?
Yeah, sort of. I guess so. So for me, it makes sense that you can measure the speed of light with two separate, like LIGO institution buildings, whatever, right? LIGO detectors. Why can't you do the same for light? Is it because of the extinction due to the atmosphere? Like, you can measure the speed of light based off of the distance, and, like the time it takes for it to get from one detector to another detector, and the time it took, right? The distance between the two. Is that not how the measure?
It's just a simultaneous arrival. It tells you that they traveled at the same speed.
Oh, okay.
Right. Right. They're only off by 1.7 seconds, right? Over 130 million light years. So, right. So that's tiny, and there should be some variation as to when they were emitted. Okay. So that's what gives us the uncertainty in the speed. Don.
You actually also have a verification of the constancy of the speed of light. I have to work out the numbers, but the fact that the kilonova dims in just 10 days in the electromagnetic spectrum, if the different parts of that spectrum were coming out at different speeds because of the motion of the source object, you would actually get much longer than 10 days for the signal to diminish. I mean, I actually thought it's really simple, but you get a very, very, very tight balance.
Well, I mean, you're also getting cooling, right?
Right, no, that's the point, is that it's all coming from the cooling. But if the speed of light were not the same for everything, that light would be spread out over probably thousands of years.
Yeah, except that depending upon the path, you could get variation in index of refraction as a function of frequency.
I'll show you.
Okay, but it's right, it's small.
Very, very tight balance.
It's very small. Okay. Let me see if I can get the NASA film to play. If not, I do have it in my browser. Nope, that's the wrong one. Hello. There we go. this one because it shows the jets, although you don't, I don't think we necessarily have a good idea as to what's happening in the remnant. And one of the leading hypotheses is that the majority of the mass got sucked into formed a black hole. Okay, so take a lot of that with artistic speculation. Okay. All right, we have to be out of this room in a few minutes, so I'll be around if anybody has any other questions. But thank you all for coming this morning.